This is the next video in the series about collision theory. In the last video, we talked about the three facets of collision theory, which were collision frequency, orientation of the molecules during collision, and the energy of the molecules during collision. And in this video, we're going to focus on that third one, energy, about how much energy it takes to break the reactant bonds. Okay, so our third facet of collision theory said it requires energy. A certain amount of energy is required in each of those collisions for the reaction to happen. So let's put that here. It takes energy to break the bonds in the reactant molecules. Most reactions involve at least one bond breaking and at least one bond forming. And the bond forming, as we saw in our picture with the magnet, is going to happen and release energy, but breaking a bond is going to take energy. And so we actually have a name for this much energy. So that minimum energy required to break the bonds, that's called the activation energy. This is like how much energy it takes to get you out of the comfy chair that you're sitting in when you have to go and do something important. It's about how much activation energy you have to put in to get out of the chair. And we abbreviate this with E sub A. That's how we'll be labeled in our diagrams. Okay, and so the question is, how big is this energy? How much energy do we need for a particular reaction? And the answer is, it depends on the reaction, as you probably expected. So we can illustrate how much energy is needed with a kind of diagram called a reaction diagram, or some textbooks call it a reaction profile. And this is going to look similar to the diagram that we previewed in the first video of this chapter. So let's draw a nice big diagram, because we're not only going to draw a diagram, we're also going to be adding pictures inside the diagram. And let's use the same reaction we did in the previous video. So that was N2O plus NO in equilibrium with N2 and NO2. So this reaction diagram is always going to have some form of energy on the y-axis. It depends, either delta H or delta G. And it's going to have the reaction progress down here. It's not strictly in time, it's just in progress from reactants to products. So our reactants are going to have some energy and our products are going to have some energy, just like we learned about in the thermodynamics chapter. So maybe we could put reactants there and products here. I'm just arbitrarily picking those. And if we were in the thermodynamics chapter, we would want to label the delta H, the difference in energy between the reactants and the products, right? We've practiced doing that. Products minus reactants, that would be our delta H. And so remember, thermodynamics and enthalpy are all about the destination. The only thing that matters is the origin and the destination, but in kinetics, we care about what happens in the middle. And what happens in the middle is that energy is required to break bonds and make this happen. So most of the time, there's going to be a hump in the middle of our trajectory. And at the top, this is going to be called the transition state. Sometimes we use this symbol, a line with two sort of sideways slashes through it. We call that the double dagger. This indicates that this maxima is unstable. The transition state is always at a local maximum. So there can be more than one transition state in a process if you have sort of a long reaction to look at, and every one of those maxima is going to be a transition state. And so these are unstable because they're very, very short-lived and they're actually undetectable. So we can't detect these with any sort of spectroscopic instrument. We can't see them with a microscope, but we know that they happen because we know how much energy is required for this reaction to happen. So we can label our activation energy on the diagram as the difference between the reactant energy and the highest point on the diagram. So in this case, it's going to be this value here. So it's the highest energy point minus the reactant energy. So if there were multiple different maxima, you would connect the reactants to whatever the highest one was. And so now let's take our pictures of the molecules and let's draw them on here so we can think about what this looks like as it's happening. So our reactants were N2O and NO2. And as we talked about in the orientation section, we know that the oxygen and the nitrogen have to collide because those are the ones that are going to be bonded in the products. And we'll write a plus since those are both present and they're not connected. So N2O and NO2 oriented in this particular way. And then over here in the products, we've got our, got green, we've got our N2, and then we've got our NO2 with the 2 oxygens attached. And then for our transition state, which I conveniently did not leave much space to draw, we know that there's going to be a bond breaking here between this nitrogen and oxygen, and there's going to be a bond forming here between this oxygen and nitrogen. So we can draw the transition state as sort of halfway between reactants and products. So I'm going to draw it over here because my planning was poor. So here we're still going to have the N2 connected as they were in the beginning, and then they're starting to become completely unconnected like they are in the products. We'll draw the oxygen atom as no longer connected, as partially connected to the N2O, so it's only partially connected, and then we'll draw it partially connected to the nitrogen that it's forming that bond to in the product. So these little dashed lines are supposed to represent partial bond. So this is our bond that's breaking between N and O. And this is the bond that's forming. And in this picture, both of these processes are happening simultaneously. It doesn't look like we break the bond and the oxygen atom is hanging out by itself, and then we form it on this part. We are actively doing both at the same time. We're starting to break that first bond and we're starting to form that second bond. When we reach the top, it could go either way. It's halfway bonded to one and halfway bonded to the other, and a slight push in either direction would cause it to go either back to the reactants or all the way down to the products. So this is the halfway point in the bond breaking and forming. And if we get a slight push in this direction, that first bond will finish breaking and that second bond will finish forming, and we will end up with our products. So sometimes we do roll back down towards the reactants. Sometimes if we don't quite get enough energy to crest the peak, we end up just staying as a reactant. And that could be because of collision energy, it could be because of collision orientation, or the frequency of collisions. Sometimes we don't quite make it over that hump. And you'll notice that I drew an equilibrium arrow here. Everything we've labeled on the diagram is for the forward reaction. Our reactants, our products, this is the delta H for the forward reaction, and this is the delta, or the activation energy for the forward reaction. We could also label those values for the reverse reaction. Right, so if we were in the reverse reaction, we would be starting here. These would be the reactants. We would end here, and these would be the products. So if we were going to draw the delta H, we would be going from product to reactant. So this time, our delta H would be a positive, would be going from low energy to high energy. And our activation energy is the difference between the reactants and the highest energy points. So these would be the reactants on the way back. So I'm going to draw a line right through everything I was just trying to say here. So this would be our activation energy for the reverse process between the reverse reactants and the highest energy point and the diagram. So you should be able to draw the activation energy and the delta H for either direction. And so our delta H numbers, just to review again, those are our thermodynamics numbers. The difference between the products and the reactants gives us information about the spontaneity of the reaction. Whether the energy change is favorable and it will react by itself. The EA, the activation energies, those are information about kinetics. And the kinetics tells us about the speed of the reaction. So for this example, forward reaction that we drew, we can see that this is exothermic. We're going from a higher energy reactant to a lower energy product. So spontaneously it would flow, but if the collisions don't have enough energy to overcome this activation energy, then the kinetics of the reaction would move at a slow speed. So you can still be spontaneous and also react slowly. And you can be non-spontaneous and react quickly. They're not necessarily related in that way. Now let's do an example of calculating how much energy that is from the picture. So let's say that our forward activation energy is 212 kilojoules. And let's say that our delta H for the forward reaction is negative 58 kilojoules. Let's try to find the reverse activation energy. This is a lot like our Q plus W problems. It's a pretty simple add subtract problem. We just need to make sure we get the signs right. So we're trying to find activation energy reverse. So it should be a positive number because we're going from low to high. And we're going to want to add the activation energy forward with the delta H of the reverse. And we don't have delta H reverse, we have delta H of forward, so we'll need to take the negative of that number. So we will do the negative of negative 58 kilojoules, and we'll add that to the 212 kilojoules. Okay, and that should give us positive 270 kilojoules. So we just want to make sure that we end up with a positive number and that we're adding the correct numbers together. Okay, and when you draw the reaction diagram, it doesn't have to be quite as epic with all of the molecules drawn in, but you do need to have those sorts of labels that we put in. So now that we've talked about how much energy you need, let's think about how many molecules actually have enough energy, because as we remember from gas laws, there's a distribution of energies of the particles. Some of them will have enough energy and not all of them will. So let's revisit our favorite diagram, the Boltzmann distribution. Our question here is, how many molecules have enough energy to react? Okay, and we can answer that question with our Boltzmann distribution, with the number of molecules at a particular energy level. Okay, so we've drawn this picture before. several times. So it's going to be number of molecules on the y-axis and the kinetic energy of the molecules on the x-axis. And it's going to look a little bit like a bell curve in shape. So let's say we're at a sort of a low temperature. We have some sort of a picture that looks like this, and it has a nice long tail on it. Remember that we can mark in the root mean square speed as slightly past the highest point of the curve. So this is the distribution of energies of the molecules. Most of them at this low temperature have a pretty low kinetic energy. But some of them have a higher amount of energy. And then what we're going to do is we're going to mark in that energy that they need. We're going to mark in the activation energy level. So I'm going to say this is how much energy we need. So if we need this value of energy, we can color in the part of the graph where the molecules are going to have enough. So this many molecules are going to have enough energy to climb over that small mountain of activation energy barrier, and the rest of these molecules are not going to have enough. So for the green curve at low temperature, if few molecules have enough energy for the reaction, then the reaction rate is going to be slow. So if we have lots of molecules that don't have enough energy and only a few molecules that do have enough energy to get over that peak, we're going to have a slow reaction. And that's no good because we want to have a fast reaction. So how can we increase the speed? How can we make it go faster? Well, we can see that if we want to increase the speed, we need to increase the number of molecules that are past this energy level. And we've talked about this the last time we used the distribution, right? We can shift the distribution by changing the energy, and we can change the energy by changing the temperature. Magic. And if you remember from our list of 4 factors that affect the rate, factor number 4 was the temperature. So let's draw a distribution for a higher temperature. Remember, we're going to shift the entire curve towards the right, and we're going to decrease the maximum height. So let's say it looks something like this. So a nice big curve, and the amount of molecules, oh, we forgot to write in the root mean square speed. There's the root mean square speed. So now the average speed is past the energy needed. So now more than half of the molecules are going to have enough energy to do the reaction. So we'll comment on that. If most molecules have enough energy, they have their collision has at least that activation energy, amount of energy. Then the reaction rate is fast. One way that we can increase the rate of most reactions is to increase the temperature, because we shift the kinetic energy of those products, of those molecules. So most of the molecules have a high energy, and we increase the number of molecules that can make it over this hump to get from reactants to products, and we increase the speed of the reaction. So we've talked about the reaction profile, the activation energy, and about the Boltzmann distribution of speeds of molecules. And in the next video, we will talk about the Arrhenius equation, which is a mathematical way of calculating the temperature's effect on the reaction rate.